Every tap, every swipe, every transaction you complete, every single query you type into a search bar, it's all generating data.
Constantly.
Yeah, not just tiny trickles, but a cascading flood of information every single second. And the truly remarkable thing, it's not just sitting there. It's being processed, organized, and retrieved in fractions of a second, making our entire digital world feel seamless and almost, well, magical. But have you ever stopped to really consider how this incredible, invisible flow of information is orchestrated behind the scenes? Welcome to the Deep Dive. Today, we're pulling back the curtain on the unsung hero of our digital lives, the foundational technology that makes all of this possible, the Database Management System, or DBMS. This deep dive is proudly presented by Knowledge Flow, and our mission is to guide you through the essential concepts that power virtually every aspect of our digital existence, from your morning coffee order to global financial markets.
And our mission for you, our listener, is to move beyond the jargon. We're going to uncover the core components, trace the fascinating history, map out the intricate architecture, and illuminate the hidden mechanisms of DBMS. It can sound like a complex topic, definitely.
Oh, absolutely.
But by the end of our conversation, we aim to transform it into clear, actionable insights that stick with you. You'll gain a fundamental understanding of the invisible architecture that truly makes modern life possible. And you might just have a few aha moments along the way.
I'm looking forward to those. So let's kick things off right at the beginning. When we talk about a database management system, or DBMS, what exactly are we referring to? What is this powerful, pervasive piece of software that runs so much of our world?
Right. Well, at its heart, a database management system is a specialized software system, essentially the central control hub for all your data. Its primary role is to give users and applications the power to easily define, create, manage, and manipulate databases.
Okay, like a master controller.
Exactly. Think of it as the ultimate librarian, security guard, and traffic controller for information all rolled into one. It provides a comprehensive suite of tools for everything from securely storing new information and efficiently retrieving existing data to ensuring the absolute integrity and security of that data. What's truly crucial is that a DBMS is specifically designed to support multiple users and applications accessing the same data concurrently.
Without tripping over each other.
Precisely. Without causing chaos or stepping on each other's toes. The benefits of this approach are immense. It ensures data consistency across the board, radically minimizes redundancy by preventing duplicate or conflicting information, and facilitates robust, reliable backup and recovery processes, which are absolutely critical in our data-driven world.
I can imagine.
Yeah. Without a DBMS, managing large shared data sets would be an absolute nightmare. Just chaos.
That's a great analogy, the ultimate librarian and traffic controller. And it wasn't always this sophisticated, was it? Here's where it gets really interesting for me. The incredible journey of how these powerful systems came to be. It's not like they just appeared overnight, fully formed.
Oh, not at all. The modern era of database management, as we know it, truly began with a pivotal technological leap. We can pinpoint a monumental moment in 1970 when Edgar F. Codd, a brilliant computer scientist at IBM, proposed the first relational model of DBMS.
Codd, right. That name comes up a lot.
It really does.
Yeah.
And this wasn't just an incremental improvement, it was a fundamental paradigm shift. It became possible largely because computing capabilities had advanced significantly in areas like memory, processing quality, and, various other storage abilities within systems.
Yeah.
Quad's genius was in decoupling the logical way we think about data from its physical storage.
Ah, okay. So separating the what from the where.
Exactly. Before this, you basically had to know where the data was physically stored to retrieve it, like knowing the exact shelf and book number in a library. Codd's model allowed you to simply ask for the book by title, and the system would figure out where it was. This foundational concept laid the groundwork for everything that followed, and allowed databases to scale and evolve in ways previously unimaginable.
And when you look at the timeline, it truly underscores just how quickly things evolved from that foundational idea. It really puts the rapid pace of innovation into perspective. So take us back to the 1960s. What was happening there before Codd's breakthrough?
Right, the 60s. Well, that era was dominated by what we call navigational DBMS. A very early and influential example was the Codicil Data Task Group, which used a manual navigation approach to data within a larger network structure.
Manual navigation, so you have to tell it exactly how to find things.
Pretty much. This meant that if you wanted to find data, you literally had to guide the system through predefined paths. Imagine following a specific set of directions in a maze. Go from record A to record B, then through this link to record C. There were three primary methods for this. using a primary key to directly jump to a record, establishing direct record-to-record or data-to-data relationships.
Like predefined links.
Exactly, predefined links.
Yeah.
Or even sequentially scanning records, which, as you can imagine, was terribly inefficient for large data sets. It was powerful for its time, but incredibly rigid. Then, as we discussed, the 1970s brought that huge paradigm shift with the emergence of relational and SQL DBMS, fundamentally changing how we interacted with data.
A real revelation.
Absolutely. The 1980s saw a wider adoption, with databases moving from mainframe giants to desktops, and the rise of object-oriented systems showcasing their increasing flexibility and ability to handle more complex data types. And finally, the 2000s ushered in the era of NoSQL and NoSQL databases, designed specifically to handle the massive scale, velocity, and diverse nature of modern web-scale data that didn't always fit neatly into traditional relational tables.
So dealing with all the messy web data.
Precisely. But today it's relational databases, building directly on Cod's original ideas, that remain incredibly dominant in the enterprise world. You see popular brands like Oracle and Mysol leading the way. Modern DBMS are absolutely essential for supporting the internal operations of countless organizations, allowing them to consolidate specialized, custom, and highly sophisticated data into one central, manageable location, which can then be efficiently maintained and operated across their entire business.
That's a great overview of the evolution. But you keep using the word database. What actually is a database in this context? Is it just a giant, really fancy Excel sheet or something far more structured?
That's a great question, and it's definitely more sophisticated than even the fanciest Excel sheet. A database is fundamentally a highly structured collection of data. This data can either be stored in a single centralized location, or it can be logically linked and accessed across multiple physical locations over a network.
Okay.
The critical differentiator is that it's organized in a very specific, optimized way that allows for incredibly efficient access, management, and retrieval. Think about a large hotel chain. Their database isn't just a simple list of bookings. It stores all sorts of detailed information, total expenditures from all their branches, customer names, their loyalty points, room availability across all properties, even maintenance schedules for individual rooms.
Wow, that's comprehensive.
Exactly. All of this diverse information is stored in one particular, centrally managed location, forming the comprehensive database for that entire brand. The structure ensures that you can quickly find, say, all customers named Smith, who stayed at the New York branch in October, and simultaneously check room availability in London, all in milliseconds.
So clearly not just a spreadsheet. Are all DBMS the same, or are there different flavors out there beyond just relational, each suited for different kinds of data or different ways of thinking about it?
Not at all. They absolutely come in different flavors, each suited for different types of data and specific use cases. They are primarily classified based on their underlying data models, which dictate how data is logically organized and stored.
Okay, data models.
Right. First, we have relational DBMS, RDBMS, which, as we've discussed, store data in tables. These tables are formally called relations. MySQL, PostgreSQL, and Oracle are classic examples that dominate this space. Then there's hierarchical DBMS, which manages data in a tree-like structure with a clear parent-child relationship where each child can only have one parent. IBM Mass is the classic example.
A bit rigid, like the early ones.
Can be, yes. You also find network DBMS, which evolved from hierarchical, mapping data in more complex graph structures, allowing for many-to-many relationships, often using pointers. Kerbo Image is a historical example here. Object-oriented DBMS integrate concepts directly from object-oriented programming, where each object in the database has both data and the methods or functions that operate on that data. DB4O is an example, often used for very complex bespoke applications.
Like CAD systems, maybe?
Exactly, like CAD or complex simulations. Finally, the more recent NoSQL DBMS are designed specifically for handling large-scale distributed data and offer highly flexible structures that don't conform to the rigid table model, such as key value, document-based, or graph databases. MongoDB and Cassandra are prominent examples in this category, often found in modern web applications. Each model has its strengths and best fits, depending on what kind of data you're dealing with and how you need to access it.
It's fascinating how diverse they are, each optimized for different problems. So if these systems are truly everywhere, where do we actually see them in action in our daily lives? Because I suspect they're far more ubiquitous than most people realize, silently powering so much of what we do.
You're absolutely right. They are omnipresent, often working silently and seamlessly in the background of almost every digital interaction. Think about your everyday life. When you check your balance or make a transfer, Banking systems rely on DBMS to securely manage customer accounts, transactions, and even complex loan details.
Makes sense. Critical stuff.
Totally. When you book a flight or check your flight status, airline reservation systems are powered by DBMS to handle all the bookings, flight schedules, and passenger information globally. In education systems, DBMS stores student records, course details, grades, attendance, and faculty information every single time you shop online.
E-commerce, definitely.
Yep. E-commerce platforms use them to manage product inventories, customer data, orders, and payment processing. Healthcare systems are critically dependent on DBMS for maintaining patient records, appointments, billing, and extensive medical histories, often across vast hospital networks. Your phone bill, your data usage, your network connection, that's all managed by DBMS and telecommunication systems, handling customer data, billing, and complex network usage patterns.
Even government services.
Oh, yes. Even government agencies use them extensively for managing citizen data, tax records, legal documents, and public services. And of course, the massive scale of social media platforms requires robust DBMS to manage billions of user profiles, interactions, and content storage. Beyond that, countless businesses use them for inventory management to track stock levels, orders, and supplier data in real time, and for human resources to maintain comprehensive employee data, payroll, and performance records. It's genuinely difficult to find a digital service today that doesn't rely on a DBMS as its backbone.
It's astounding how much they underpin. So what's the big payoff? What's the ultimate advantage, the core benefit of using a DBMS instead of just, say, meticulously organized file folders or a bunch of intricately linked spreadsheets? What problem does it fundamentally solve?
The advantages are profound and truly make DBMS indispensable for any serious data management. One of the biggest and most revolutionary is data independence.
Data independence, okay.
Imagine if every application you used, from your banking app to your social media, needed to know the exact physical location and format of every piece of data. That would be a nightmare. Data independence means your applications are independent of the specific details of how data is physically represented or stored. The conceptual schema, how you logically define your data, is totally independent of the physical storage decisions or even minor logical design changes at a lower level.
So you can change the storage without breaking the app.
Exactly. This makes systems vastly more flexible, easier to update, and future-proof. Another critical benefit is centralized data administration. A DBMS provides a common, consistent platform for a large collection of data that can be shared by many users and applications. This greatly facilitates maintenance. A good database administrator, or DBA, effectively shields end users from the complexities of fine-tuning data representation, optimizing performance, and performing those crucial periodic backups.
The unsung heroes we mentioned.
Absolutely. Furthermore, data integrity and security are paramount. A DBMS maintains this through robust view mechanisms, which allow you to present customized subsets of data to different users, and powerful authorization facilities, which provide fine-grained access control. It also offers vital functions required by modern applications, including excellent concurrency control. This allows the DBMS to execute transactions in an interleaved way to achieve efficient performance, but it meticulously schedules them to ensure that problematic operations like two users trying to update the same record simultaneously in a way that causes errors are not allowed to proceed.
Managing the traffic again?
Precisely. And critically, a DBMS provides crash recovery, an essential function that ensures data is not lost or corrupted in the event of any system failure. Finally, it offers high-level query facilities, making it possible to retrieve and manipulate even highly complex data with relative ease using powerful query languages like SQL.
It sounds like the DBA is truly the unsung hero, the wizard behind the curtain, making sure these complex systems run smoothly and all those benefits are realized. What exactly does a database administrator do? What's their day-to-day like?
You're absolutely right. The database administrator, or DBA, plays a truly critical role. They are the architects, the guardians, and the performance engineers of the database. A major part of their job involves designing the logical and physical schemas of the database, or at least guiding the teams that do. This is about shaping the very structure of the information.
The blueprint people.
Yeah, exactly. A huge responsibility also involves managing security and access authorization, rigorously ensuring that only authorized individuals and applications can access specific data, and that sensitive information remains protected when failures inevitably occur.
Which they do.
The DBA is on the front lines, orchestrating recovery from those failures and ensuring continuous data availability. And crucially, they are constantly monitoring and fine-tuning the system to ensure quality performance, keeping everything running at optimal efficiency, even as data volumes and user demands grow. They are the backbone, ensuring the reliability and speed we've come to expect.
Now that we have a solid grasp of what a DBMS is and why it's so vital, let's peel back another layer. How are these complex systems actually put together? When we talk about the architecture of a database system, what are we really talking about? Is it like the physical building?
It's a good analogy. Database system architecture refers to the overall design and structure of a database system. Think of it as the blueprint for how the entire system functions. It explicitly outlines how data is stored, how it's processed, and critically, how it's accessed by users and applications. This blueprint visually highlights the relationships between all the key players: the users interacting with the system, the applications they use, the DBMS software itself, and the underlying hardware where the data resides. A well-designed architecture is absolutely fundamental because it directly impacts so many critical aspects: the system's performance, how scalable it can be to handle growth, the level of data security you can provide, and that crucial concept of data independence we mentioned, which allows flexibility and easier updates.
Right, data independence again.
Exactly. Without a solid architectural blueprint, a database system can quickly become unwieldy, inefficient, and unreliable.
So it's the foundation of everything that follows. What are the core goals that drive the design of these architectures? It sounds like there are many factors to balance, almost like designing a city, as you said.
Exactly, like designing a city for optimal flow and functionality. There are several key objectives that designers aim for. First, they want to provide robust data extraction and data independence, meaning changes at one underlying level of the database shouldn't necessarily ripple up and impact applications or users at higher levels.
Keep things separate.
Right. Second, they aim to support multiple views of the data for different users. A marketing analyst, for example, might need a different view of customer data than someone in finance, and the architecture must accommodate that. Third, the design must enable efficient data access and management, ensuring quick retrieval and updates for both simple and complex operations. Fourth, it needs to secure and isolate user operations, protecting sensitive data from unauthorized access and preventing one user's actions from corrupting another's. And finally, the architecture must inherently ensure reliability, consistency, and scalability to gracefully handle ever-growing data volumes and increasing user demands.
That makes perfect sense. And speaking of layers, let's unpack one of the most fundamental frameworks, the famous three-level architecture. This really shapes how we think about database design, doesn't it?
It absolutely does. It's a cornerstone concept, formally established by the Ansys Park framework. It essentially divides the database into three distinct conceptual levels, each addressing a different perspective: how users perceive the data, how the entire database is logically structured, and how the data is physically stored on disk.
Okay, 3 levels. What's the top one?
The first is the external level, or view level. This is the closest level to the end users and applications. It shows only how each specific user or application views the data. The true power here is that different users can have vastly different customized views of the exact same underlying database, tailored precisely to their needs and security clearances.
So I only see what I need to see.
Exactly. For instance, a sales manager might only see customer names and sales figures, while a warehouse manager sees inventory levels. This level also provides crucial security by allowing fine-grained control over access to particular data. A user only sees what's relevant and authorized for their job, nothing more. Below that is the conceptual level, or logical level. This is the bird's eye view. It describes the entire database logically from a global enterprise-wide perspective. It defines all the entities like customer or product, their attributes, the relationships between them, along with any constraints and data types.
The big picture.
Precisely. A key aspect of this level is that it completely hides the physical storage information from users and even most developers. It's the complete abstract blueprint of the entire database, and it's typically maintained and managed by the database administrator, or DBA. Finally, at the very bottom, we have the internal level, or physical level. This is where the bits and bytes reside. It reports exactly how data is actually stored in the physical storage devices, things like hard drives or solid-state drives.
The nitty-gritty hardware stuff.
Exactly. This level covers the nitty-gritty details such as file structures, specific indexing strategies used to speed up data access, and data compression techniques. The primary focus here is on maximizing performance optimization and storage efficiency, ensuring that data can be accessed and stored as quickly and compactly as possible. These 3 layers ensure a powerful separation of concerns, leading to that critical data independence.
So within that architecture, what are the individual components, the hidden cogs and gears working behind the scenes to make all these levels function seamlessly?
Ah, the components. Within that sophisticated architecture, there are several key components that work in concert. The query processor is essentially the brain that interprets and executes the SQL queries that users submit. It figures out the most efficient way to fulfill your data request.
The optimizer we'll talk about later.
Part of it, yes. The DDL compiler processes all your data definition language commands, like create table or alter database, essentially defining the database's structure. Similarly, the DML compiler takes care of data manipulation language statements, such as insert or update, handling the actual changes to data. The transaction manager is a crucial guardian. It ensures that all database transactions are executed correctly, adhering to the critical ACID properties we'll discuss later, guaranteeing reliability.
ACID, okay.
The storage manager is responsible for the overall storage and retrieval of data from the disk, acting as the interface between the DBMS and the raw data. And finally, the buffer manager handles the crucial task of controlling memory disk data transfers, optimizing how data moves efficiently between the computer's fast RAM and slower persistent storage. These components are constantly communicating and coordinating to fulfill user requests.
And beyond that three-level conceptual model, how are DBMS actually deployed and structured in terms of their overall architecture? Are they always housed in one central location, or can they be spread out?
That's a great question about real-world deployment patterns. There are four main types of DBMS architectures in terms of how they are physically set up. First, we have centralized architecture. In this setup, all data and the DBMS software itself reside entirely on a single system, like a powerful server. Users typically access it via simple terminals or lightweight client applications.
Simple, but maybe not scalable.
Exactly. It's straightforward to set up and manage, but its main limitation is scalability. It can struggle significantly when trying to handle a very large number of users or massive data growth. Second is the ubiquitous client-server architecture. This is extremely common in enterprise applications. Here, clients, which could be your desktop applications or web interfaces, send requests to a central database server. The server then processes those queries, performs the necessary operations, and sends the results back to the client.
That sounds more familiar.
It is. This model excels because it distributes the workload effectively, allowing clients to handle the user interface and server to focus on data management, leading to better resource utilization and scalability than a centralized system. Third, there's the distributed architecture. As the name suggests, in this model, data is deliberately spread across multiple physical locations, and each location has its own local DBMS. These individual database systems are connected via a network, working together as a single logical database.
So the user doesn't know where the data actually is.
Ideally, yes. This architecture supports powerful concepts like location transparency, meaning users don't need to know where the data physically resides, and data replication, where copies of data can exist in multiple places for redundancy, fault tolerance, and improved performance. It's often used for large-scale, geographically dispersed operations. And finally, a rapidly growing and incredibly popular architecture is cloud-based architecture. Here, databases are hosted on cloud platforms and managed by cloud providers like Amazon Web Services, Google Cloud, or Microsoft Azure.
AWS, Azure, GCP.
Precisely. This offers significant advantages like extreme scalability, allowing you to easily expand or shrink resources as needed, often automatically. It provides global accessibility, meaning users from virtually anywhere in the world can often access the data quickly, and it can be highly cost-efficient as you typically only pay for the resources you consume. Amazon RDS, Google Cloud SQL, and Microsoft Azure SQL Database are prominent examples of this model.
So we've got the layered design, the internal components, and the deployment models. But how does it all actually flow? From the moment you type a query into an application to getting your results back, it sounds like there's a whole intricate dance happening behind the scenes.
It truly is a beautifully choreographed sequence designed for speed and reliability. When a user or an application submits a SQL query, the very first step is that the query processor springs into action. It analyzes your query, parses it, and then crucially, optimizes it. It figures out the most efficient way to actually get the data you're asking for, considering all available indexes and data paths.
Okay, the smart part.
Exactly. Once that optimal execution plan is determined, the transaction manager steps in. Its job is to verify that the operation can be carried out securely and correctly, meticulously managing the ACD properties of the transaction, ensuring it's atomic, consistent, isolated, and durable. After that, Storage Manager takes over, interacting directly with the physical storage layer to either retrieve the requested data from disk or update existing data. Finally, once the data operation is complete and validated, the result is sent back to the user or the application that initiated the query, completing the entire data operation cycle in a blink.
What's the big win for having this sophisticated, multi-layered architecture? It seems like a lot of complexity, but there must be a huge payoff for building systems this way.
Oh, the payoff is substantial and fundamental to building robust, long-lasting database systems. First, there's significant modularity. Because the system is divided into distinct layers and components, it's much easier to maintain, troubleshoot, and update individual parts without causing a ripple effect across the entire system.
Easier fixes.
All right. Second, it profoundly enhances security. With different layers, you can implement fine-grained access control at various points, controlling precisely who can see what data and how it can be manipulated, protecting sensitive information. Third, and critically important, is data independence. This layered approach minimizes the impact of structural changes.
There it is again.
Yep. If you change how data is physically stored at the internal level, it doesn't necessarily require rewriting all your applications that interact with the logical view, saving immense development effort. Fourth, it brilliantly facilitates concurrent access. Multiple users can access and modify data securely and simultaneously without interfering with each other's operations or corrupting the data. And finally, it provides immense flexibility and scalability, allowing database systems to adapt to new technologies, support distributed environments, and scale up to handle ever-increasing volumes of data and users, especially crucial in today's cloud-first world.
So we've talked about what a database is and how the system that manages it is built. But before data even goes into the system, how do we think about and structure the data itself? This is where data models come in, right? It's like the initial blueprint of the information.
Precisely. Data models are absolutely crucial. They provide the conceptual framework that explains how data is structured, stored, and ultimately handled within a database. Think of it as the original blueprint for your data, even before you start building the actual database. A data model defines the specific data elements you'll be storing, how relationships exist between those different elements, and the rules that govern how the data is organized. They are utterly essential in database design because they bridge that critical gap between how we perceive information in the messy, unstructured real world and how that information is digitally represented and managed within a highly structured database system.
Making sense of the real world for the computer.
In essence, yes. They ensure that the digital representation accurately reflects the real-world facts you're trying to capture.
Why are these data models so absolutely crucial in the design process? Couldn't you just jump straight to creating tables and columns and figure it out as you go?
While you technically could jump straight to creating tables, it would be a recipe for chaos and disaster in anything but the simplest, most trivial cases.
Okay, fair enough.
Data models are crucial because they offer several foundational benefits. They first help tremendously in data extraction and representation, allowing designers to clearly identify exactly what information needs to be captured and how it should be represented. They directly assist in robust database design and structure by providing a clear, high-level abstract view of the data before you get bogged down in the nitty-gritty implementation details. This clarity, in turn, provides consistency, clarity, and accuracy of data throughout the system, minimizing ambiguity and errors. A well-defined data model offers a better, more solid base for implementing databases, ensuring that the final system is robust, maintainable, and truly meets the business requirements. And ultimately, they enable efficient data manipulation and access because the data is organized in a logical, predictable, and optimized way, making it easy for users and applications to find and use the information they need.
What are the big picture categories of data models we should know about? How do we classify these different ways of thinking about data?
Data models can broadly be classified into three main categories based on their level of abstraction and how they represent data. First, we have object-based data models. These models are closer to how humans perceive information, using a conceptual setup that focuses on entities which are real-world objects, like a student or a cursor attributes, and the relationships between them.
More conceptual.
Exactly. Second, there are record-based data models, which are a bit closer to how data is stored in a DBMS. They focus on fixed-format records with defined fields, like rows and columns in a table. Finally, we have physical data models, which are the lowest level of abstraction, and explicitly define how data is physically stored and accessed in the underlying hardware down to the byte level.
Let's dive into the object-based data models first. They sound like they help conceptualize things at a higher level, right?
They absolutely do. The most widely known and used in this category is the Entity Relationship ER model. This model represents data in terms of entities which are the things or objects in your domain, like student, professor, or Of course, their attributes, which are the properties of those entities, like a student's name or ID, and the relationships between these entities, such as a student enrolls in a course.
Ah, the classic ER diagram.
Exactly. ER diagrams are incredibly powerful visual tools that help in showing the database structure at a conceptual level, making it very clear how different pieces of information relate before you write a single line of code. For example, a student entity might have attributes like name, ID, and syllabus. Another important object-based model is the object-oriented data model. This one directly incorporates concepts from object-oriented programming, such as classes, inheritance, and encapsulation. In this model, each object in the database not only holds data, but also includes methods, which are the functions or operations that can be performed on that data.
So data and behavior together.
Precisely. This tight coupling of data and behavior makes it particularly well suited for complex applications, such as multimedia databases or computer-aided design or CAD systems, where the behavior of the data is as important as its structure.
And then there are the record-based data models, which have been widely used in commercial systems historically and even today, especially the relational model. Can you tell us about those, starting with the earlier ones?
Right. The record-based models are indeed very prevalent, especially historically, in commercial DBMS, as they are closer to how data is physically organized. First, we have the hierarchical model. This organizes data in a rigid, tree-like structure, establishing clear parent-child relationships. The key rule here is that each child can have only one parent.
Like an org chart.
Exactly like an org chart. It was known for being fast and simple for specific applications, like bill of materials in manufacturing. But its main drawback was a severe lack of flexibility, making it hard to represent complex relationships where a child might have multiple parents. An example would be a company structure where each department has employees, but an employee only belongs to one department. Next is the network model. This evolved directly from the hierarchical model, designed to overcome its limitations. It organizes data as a more flexible graph structure, allowing for many-to-many relationships, using concepts like sets and pointers to link data records.
More flexible, less tree-like.
Correct. This meant a child could have multiple parents, making it more flexible than the hierarchical model. An example here could be a student enrolled in several courses, and a single course having many students, a true many-to-many scenario that the hierarchical model couldn't easily handle. And then the true game changer among record-based models, the relational model. This is the one that really revolutionized database management and remains dominant. It represents data in the form of simple, intuitive tables, often called relations.
Rows and columns.
Rows and columns, exactly. Each table has rows, known as tuples or records, and columns, known as attributes or fields. Relationships between different tables are established using common columns called keys, allowing for incredibly powerful and flexible data connections. This model supports extremely powerful querying capabilities, primarily through SQL or structured query language. It is by far the most commonly used model in modern DBMS today, with examples like MySQL, PostgreSQL, and Oracle dominating the landscape because of its simplicity, flexibility, and robust theoretical foundation.
Finally, the physical data models. These are usually behind the scenes, hidden from the end user, but absolutely essential for optimization and how the database actually performs. What are they about?
Right. The physical models are the most granular and lowest level. They define precisely how data is physically stored within the internal storage of the database system. This includes incredibly specific details like how files are structured on disk, where indexes are placed to speed up lookups, how data is organized into blocks on the storage media, and the specific access paths used to retrieve data.
So deep down in the hardware.
Deep down. While not directly used or seen by end users, you don't interact with these details when you query a database, they are absolutely critical for database performance tuning. They are essential tools for database administrators and system developers who need to optimize the underlying storage for maximum speed and efficiency. Think of them as the detailed schematics for the engine of a car. The driver doesn't see them, but they dictate how fast and smoothly the car runs.
Okay, let's zoom in on the relational model because it has truly revolutionized how we handle data and is so dominant today. We hear about relational databases all the time, but what are the precise components? What makes them tick?
Yeah, the relational model is built on a very precise vocabulary and a beautifully simple structure. A relational database itself is fundamentally a collection of several tables, which are also formally called relations table. This is the very reason for the existence of the term relational database.
Okay. Relation means table.
Essentially, yes. Each of these tables is a physical representation of an entity, like a customer or a product, displayed in a tabular format. They consist of columns, also known as fields or attributes, which describe the characteristics of an entity, for example, a name or age column. And they have rows, which are the individual values or data instances, often called records or tuples, representing a single complete entry. Within this structure, we define several key components. A relation schema is essentially the blueprint for a single table. It specifies the name of the table and the names and types of its columns. A relational database schema then describes the blueprint for the entire collection of tables and how they relate to each other.
The overall structure.
Right. A domain defines the set of all possible values for a particular attribute. For instance, the domain for an age attribute might be all positive integers. An attribute is a characteristic or property, like customer name or order date. An attribute domain explicitly shows the data type associated with that column, such as an integer, a string, or a date. A relation instance is simply the actual data contained in a table at any given moment, the set of records or rows. Relation cardinality refers to the count of the total number of records or rows currently in a table. And relation degree is the number of attributes, or fields columns, present in that specific table.
Cardinality is rows, degree is columns. Got it.
Exactly. Relationships exist both between the columns within a table and, crucially, among different tables. These relationships can logically take three primary forms. One-to-one, where a single record in one table corresponds to a single record in another, like one employee having one specific parking spot. One-to-many, where one record in the first table can be associated with multiple records in the second, such as one customer placing many orders. And many-to-many, where multiple records in one table can relate to multiple records in another, like many students enrolling in many courses. Today, databases with these relational attributes have indeed become the favorites for data storage due to their elegant simplicity, incredible flexibility, and powerful query capabilities. It's also incredibly helpful to see the equivalence between the terms used in SQL, the language we use to interact with these databases, and the more theoretical terms used in the relational database RDB model.
Ah, the translation.
Yeah. What we call a row in SQL is conceptually a tuple, or record in RDB, representing a single item or entry. A column in SQL is an attribute or field in RDB, which is a labeled element of a tuple describing a characteristic. A table in SQL is a relation in RDB, defined as a set of columns and rows. And a ViewW in SQL, which is a virtual table created from a query, is called a derived relvar in RDB, essentially any set of tuples or the dynamic response to a query. This foundational consistency is part of what makes the relational model so robust.
What makes the relational database management system so powerful and widely adopted? Beyond just its tabular structure, what are its superpowers?
Its power truly comes from several critical features that address core data management needs. First, data integrity is a cornerstone. RDBMS strictly maintains accuracy and consistency through a system of constraints and rules, ensuring your data remains reliable and valid.
Keeping the data clean.
Exactly. Second, that powerful concept of data independence means you can modify the underlying database structure without necessarily affecting how applications access the data, which is a huge benefit for maintainability and longevity of systems. Security is robustly built in, with fine-grained access controls and user roles protecting sensitive information from unauthorized access. Concurrency control ensures that multiple users can access and modify data simultaneously without any conflicts or problems, maintaining data consistency even under heavy load. Normalization is a key feature that helps manage data to minimize redundancy and dependency, leading to more efficient storage, faster queries, and fewer inconsistencies. And finally, scalability and flexibility are inherent, allowing RDBMS to easily handle growing data volumes and complex queries that evolve over time, making them adaptable to almost any business need.
And the language that makes it all tick, SQL. We've mentioned it a few times, but it's absolutely central to everything we've been discussing. It's the universal translator for relational databases.
That's right. SQL, or Structured Query Language, is the undisputed standard language for interacting with relational database management systems. It's essentially the universal language you use to talk to an RDBMS. SQL empowers users to perform all fundamental data operations, creating new data entries, retrieving existing information, updating records, and deleting data within a database system.
CRUD operations, basically. Create, read, update, delete.
Exactly. The CRUD operations are core DML functions within SQL. It acts as the essential interface, making data handling simpler and far more efficient for both developers and end users. Its prevalence is evident in its common use across almost all relational database management systems, including major players like Oracle, MySQL, Microsoft SQL Server, PostgreSQL, and SQLite. If you're working with relational data, you are almost certainly working with SQL. SQL isn't just one thing. It's a family of sublanguages. You have the data definition language, DDL, for defining database structures like create, alter, and drop commands. Then there's the data manipulation language, DML, used for interacting with the data itself, including select, insert, update, and delete. Data control language, DCL, handles access rights with grant and revoke. And finally, transaction control language, TCL, manages transactions with commit and rollback.
Different tools for different jobs.
Precisely. For instance, a simple DDL command might look like this. Create table students. Student NT, primary key, named varchar100, AGINT, grade J1. This command literally defines and creates a new table named students with specific columns and their data types, even setting student AD as the unique identifier. It's concise, powerful, and universally understood by RDBMS.
Summing up the relational model, what are its ultimate benefit for us, the users, and the organizations that rely on this technology? Why has it stood the test of time?
The ultimate benefits of RDBMS are profound for anyone dealing with data, and they are why it has endured. Its simple structure, presented in intuitive tabular form, makes it remarkably easy to understand and use, even for highly complex data sets.
Approachable.
Very. The efficiency of SQL querying enables superior data manipulation and retrieval, allowing users to extract precisely what they need, quickly and flexibly. Data consistency is strictly enforced through a system of constraints and rules, meaning you can trust the accuracy and validity of your information, which is critical for business decisions. Reduced redundancy, achieved through normalization, minimizes duplicated data, saving storage space and preventing inconsistencies that can lead to errors. Crucially, RDBMS offers robust support for transactions, ensuring dependability through the ACD properties, atomicity, consistency, isolation, and durability, meaning your data operations are always reliable and atomic. And finally, strong data security is built in, with user roles and permissions restricting unauthorized access to sensitive information, protecting privacy and business assets. It's a really solid foundation.
We've touched on SQL, but let's do a proper deep dive on this critical language itself. What exactly is SQL, and why is it so incredibly prevalent across the digital landscape?
All right, SQL Structured Query Language. It's the undisputed standard programming language, specifically designed for managing and operating relational databases. It's essentially the universal language you'd use to talk to an RDBMS. SQL empowers users to perform all fundamental data operations, creating new data entries, retrieving existing information, updating records, and deleting data within a database system.
The language of data.
You could say that. It acts as the essential interface, making data handling simpler and far more efficient for both developers and end users. Its prevalence is evident in its common use across almost all relational database management systems, including major players like MySQL, Oracle, SQL Server, PostgreSQL, and SQLite. If you're working with relational data, you're almost certainly working with SQL. It's the lingua franca of structured data.
What are the standout features that make SQL so powerful and widely adopted, even decades after its inception?
SQL's power comes from a potent combination of elegant design and robust functionality. First, it's remarkably simple and easy to learn its fundamental commands, making it accessible to a wide range of users, not just programmers.
Relatively speaking, of course.
Yes, relatively speaking. Yet, despite its simplicity, it can handle incredibly complex queries, allowing you to retrieve and manipulate highly specific subsets of data from vast interconnected tables. It provides comprehensive data manipulation and definition capabilities, meaning you can define your database structure, populate it with data, and then modify or delete that information as needed. Crucially, SQL supports features that ensure data integrity and security, helping to maintain the accuracy and protection of your valuable information. It's also largely platform independent, meaning the same SQL commands often work across different RDBMS. And importantly, it uses standard syntax, which contributes significantly to its widespread adoption, interoperability, and the vast community of developers who understand it.
Let's break down the different types of SQL commands, the 5 major categories that define how we interact with databases. This really clarifies its full range of capabilities.
Absolutely. SQL commands are systematically classified into 5 major categories, each serving a distinct purpose in database management. First, we have Data Definition Language, or DDL. As its name suggests, DDL commands are used to define and manage the structure of your database. These are the commands you use to build the framework. Common commands include create, which you use to build a new table or even an entire database, alter, for modifying existing database objects like adding a new column to a table, drop, to completely delete database objects such as a table or a view, and truncate, which is used to efficiently remove all records from a table while keeping the table structure intact.
Like setting up the filing cabinet.
Exactly. For example, create table students, ID int, name varchar 50, age int. This command literally defines and creates a new empty table named students with 3 columns, ID, name, and age. Next is data manipulation language, or DML. These commands are all about manipulating the actual data within your tables. Once your structure is defined, DML is how you fill it and change it.
Putting files in the cabinets, changing them.
Perfect analogy. The most common DML commands are insert, used to add new rows of data into a table, update, to modify existing data in one or more rows, and delete, to remove specific rows of data from a table. So if you wanted to add a new student, you'd use insert into students, ID, name, age, values 1, Alice, 20. This command puts a new record into your students table. Third, we have data query language, or DQL. This category is primarily for querying or retrieving data from the database. It's how you ask the database questions.
Finding the files you need.
Precisely. The single most fundamental DQL command is select. It's what you use to pull specific information from one or more tables based on various criteria. For instance, select name, age from students who are age 18. This query asks the database to retrieve just the name and age of all students who are older than 18. Fourth is data control language, or DCL. DCL commands are used to control access to the data, managing permissions and security within the database. It's about who can do what.
Who gets the keys to which cabinet?
You got it. The 2 main commands here are grant, which is used to give specific access rights to a user or role, like allowing them to read a table, and revoke, which is used to remove those previously granted access rights. An example would be grant select on students to user 1. This command gives user 1 permission to only read data from the student's table, preventing them from making changes. And finally, we have transaction control language, or TCL. These commands are crucial for handling transactions in a database, ensuring data integrity during multiple operations, especially when many changes are happening.
Making sure changes are safe and complete.
Exactly. Commit is used to save all changes made during a transaction, making them permanent in the database. Rollback is used to undo all changes made during a transaction, reverting the database to its state before the transaction began. Save point allows you to create a temporary point within a transaction to which you can partially roll back, rather than undoing the entire transaction. A common sequence would be begin. Update students set age equals 21 where ID equals 1. Rollback. Here, an attempt to update a student's age is made, but then completely undone, as if it never happened, ensuring data consistency if something goes wrong midway.
Beyond basic commands, SQL offers incredibly powerful operators and clauses for filtering, sorting, and combining data in incredibly precise ways. It's where the real magic of data retrieval happens.
That's right. SQL's true expressiveness comes from these building blocks that allow for nuanced data manipulation. When it comes to operators, you have comparison operators like ACCULAR, ACCUL, and for comparing values. Logical operators such as AND or AIR, and not for combining multiple conditions, letting you build complex logic. And range and pattern matching operators like between for values within a numerical or date range, and for checking if a value exists within a specified list, and like for pattern matching using wildcards, useful for searching text.
The like is super useful for searching names and things.
Absolutely. As for clauses, these modify the behavior of your select statements, allowing you to shape the results. The where clause is fundamental, used to filter individual records based on a specified condition, like where age 18. Order by is used to sort the result set, typically in ascending or descending order, making your data readable and organized. Group by allows you to group rows that share a common property, typically used in conjunction with aggregate functions to perform calculations on each group, like finding the average age per department. And having is similar to where, but it specifically filters groups of rows after the group by clause has been applied, allowing you to filter based on aggregated results.
Joins are one of the most powerful features in SQL, allowing you to bring together data from disparate tables. How do they work, and what are the main types we commonly encounter?
Joins are indeed incredibly powerful and essential for working with relational data, which is often spread across multiple tables. Their core purpose is to combine data from 2 or more tables based on related columns. This is how you connect, say, a student's ID in one table to their course enrollments in another, or a customer's ID to all their past orders.
Stitching the tables together?
Precisely. There are several common types of joins. An inner join is the most common and often the default. It returns only the rows that have matching values in the specified related columns from both tables. If a record in one table doesn't have a corresponding match in the other, it's simply excluded from the result. This gives you the intersection of the data. A left join, often called left outer join, is different. It returns all rows from the left table, the first table specified, and any matched rows from the right table. If there's no match for a left table row in the right table, the columns from the right table will simply have NLL values.
So you keep everything from the first table listed.
Exactly. This is great for showing all of one thing, even if it doesn't have a related item. Conversely, a right join, or right outer join, does the opposite. It returns all rows from the right table and any matched rows from the left table. If no match on the left, those columns will be AL. And a full join, or full outer join, returns all rows when there is a match in either table, essentially combining the results of both left and right joins. If a row doesn't have a match in the other table, the columns for that table will be NL. This gives you a complete picture of all data from both tables, matched where possible.
Gives you everything.
Pretty much. Here's a simple example of an inner join. Select students. Name, courses. Course name from students inner join courses on students.id. Courses, student ID. This query would combine student names with their corresponding course names, but only for students who are actually enrolled in a course and courses that have enrolled students. If a student isn't enrolled in any course, or a course has no students, they wouldn't appear in the result of this particular join.
How do we ensure the data stays clean, consistent, and adheres to specific rules within the database itself, almost like setting up guardrails? This sounds like a job for constraints.
You've hit on a critical point. Constraints in SQL are precisely those rules that are applied to table columns, or sometimes the whole table, to ensure data integrity and prevent invalid data from being entered. They act like guardrails, maintaining its accuracy and reliability.
Keeping bad data out.
Exactly. We have several types, each serving a vital purpose. A primary key is probably the most fundamental. It's a column or a set of columns that uniquely identifies each row in a table. It must contain unique values and cannot contain NLL values. Think of it like a unique ID card for every single record. A foreign key establishes link between two tables, ensuring referential integrity. This means a value in the foreign key column in one table must exist as a primary key in another related table. It prevents orphan records.
Maintaining those links between tables.
Correct. A unique constraint ensures that all values in a specified column or set of columns are unique across all rows, preventing duplicates for that specific column, even if it's not the primary key. A not null constraint simply ensures that a column cannot contain NLL values, forcing you to provide a value for that column. And a check constraint ensures that all values in a column meet a specific condition you define, like ensuring an age is always positive or price is above 0. For example, if you're creating a table for cars, create table cars. ID and int at primary key, car name varchar, not null, model int check, model 2023. Here, ID is a primary key for unique identification. Car name cannot be empty, and the model year must be 2023 or later. These constraints automatically enforce your business rules at the database level.
And what about some more advanced features that streamline data access and complex queries, like virtual tables or queries nested within other queries?
SQL indeed offers powerful advanced features that significantly enhance flexibility in data analysis. One such feature is a view. A view is essentially a virtual table. It doesn't physically store data itself. Instead, it's created from a select query and acts like a saved query that you can interact with as if it were a real table.
Like a save search you can query again.
Exactly. When you query a view, it simply executes its underlying select statement to retrieve the data dynamically. Views simplify complex queries, provide data security by allowing you to show only relevant columns or rows to specific users, and can aggregate data, making complex reports much simpler. For instance, create view new cars as select from cars where model 2023 creates a virtual table named new cars that only shows cars manufactured before 2023 without duplicating any data. Another advanced and incredibly versatile feature is a subquery. As the name implies, a subquery is a query nested within another SQL query. It can be used in various clauses like select, from, where, or having. Subqueries allow you to perform operations that depend on the results of another query, enabling very powerful and specific data retrieval.
A query inside a query.
Right. For example, select name from cars, where model, select AVG model from cars. This query first calculates the average model year of all cars using the inner subquery, and then the outer query selects the names of cars that have a model year greater than that calculated average. SQL also provides many built-in functions to achieve calculations and transformations directly on your data within queries. These include powerful aggregate functions like seam, AVG, count, A&E, and max, which perform calculations on sets of rows. There are versatile string functions like concat, substring, and length for manipulating text data, and robust date functions such as now, curDate, and dateDiff for working with dates and times, performing calculations like finding the number of days between two dates. These functions are invaluable for data analysis and reporting directly within your queries, minimizing the need for external processing.
We've covered what a DBMS is, how it's structured, and how to communicate with it using SQL. But before you even write a single line of SQL or set up a table, how do you design a database effectively from the ground up to ensure it's efficient and robust? This initial planning sounds absolutely critical.
It is absolutely critical. Database design is a multifaceted discipline, much like architectural design for a building. It encompasses various aspects of designing an entire database system, focusing first and foremost on the logical design for the base data structures that will be used to store information.
Tables and views, mostly.
Right. In the relational model, this means designing tables and views. But the term database design isn't just about these static structures. It also refers to the overall iterative process of designing not only these base data structures, but also considering the queries and applications that will interact with the database. It's about creating an efficient, reliable, and scalable system for managing information, one that will serve your needs not just today, but for years to come.
So what's the step-by-step process one should follow to design a database effectively without missing critical steps that could lead to problems down the line?
There's a well-defined process to ensure a robust and functional database design. It usually goes something like this. 1. The very first preparatory step is to determine the necessity of the database. Do you even need one? What specific problems will it solve? What goals will it help you achieve? Clearly defining the purpose is paramount.
Step 0. Why are we doing this?
Exactly. 2. Next, you need to point out and arrange the information required. This involves thoroughly collecting all types of information that needs to be recorded, stored, and managed in the database. What entities are important? What properties do they have? 3. Then it's time to divide and rule by making the information got in form of table. This means logically dividing the collected information into core entities or subjects that will become your tables. Think of entities as the main nouns in your system, like customers, orders, or products.
Breaking it down.
4. Following that, you'll be turning information into columns. For each identified table, you decide exactly what specific pieces of information need to be stored within it. Each piece becomes a field displayed as a column. For example, a customer's table might have columns for customer ID, customer name, email, and address. 5. A crucial step is to specify primary keys. A primary key is a set of columns used to uniquely identify each individual row within a table, ensuring no two rows are identical. It's the unique identifier for every record.
The unique ID.
Right. 6. Then comes setting the table relationships. This is where you connect your tables. You decide how data in one table relates to data in another, whether it's a one-to-one, one-to-many, or many-to-many relationship, defining how these entities interact. 7. After the initial design, you refine the designing. This involves analyzing the design for error correction, checking for inconsistencies, and making adjustments as needed. This is often an iterative process where you go back and forth between steps.
Checking your work.
Absolutely. 8. Finally, and crucially, you use the normalization rules. These formal rules are applied to ensure tables are structured in an ordered way, systematically minimizing redundancy and improving data integrity and efficiency. We'll definitely dig into normalization more.
Okay, we've talked about entities, attributes, and relationships throughout this deep dive. Just to be perfectly clear for our listener, what exactly do those mean in the context of database design?
Right. Good clarification. These terms are indeed fundamental to understanding database design at a conceptual level. An entity is an object existing in the real world that is distinguishable from other objects, like a student, a course, or a book. It's a thing you want to store information about.
The nouns.
The nouns, exactly. An attribute is a property or characteristic of an entity. For example, name, ID, and age are attributes of a student entity. A domain is the set of all possible values for an attribute. For instance, the domain for an age attribute might be all positive integers between 0 and 120. A relationship is an association between two or more entities, showing how they are connected or interact, like a student enrolls in a course.
Connections.
Right. And then you have sets of these. An entity set is just a collection of similar entities, like all the students. A relationship set is a collection of similar kinds of relationships, like all the enrolls in instances. We also talk about the type of relationship, like one-to-many relationship, where one entity can be involved with many of another, one customer, many orders, or many-to-many relationships, where many of one entity can be involved with many of another, many students, many courses.
There are also different types or levels of database design itself. Can you walk us through those from the abstract to the concrete?
Yes. Database design typically progresses through distinct conceptual stages, moving from a very high-level abstract view down to the physical implementation details. The first is the conceptual schema. At this stage, the database designer focuses purely on understanding the data that needs to be stored and determines the dependencies and relationships within that data. It's a technology-agnostic, human-readable view of the data, often expressed through diagrams. Changes here can affect data not immediately visible, so it's about understanding the core meaning.
High-level blueprint.
Exactly. Once those relationships and dependencies are clear, the next step is logically structuring data. Here, the information is arranged into a logical structure that can be mapped to the specific storage objects supported by the chosen DBMS, like tables, columns, and relationships in a relational database. This is where you decide on table names, column names, and their relationships, but still without worrying about physical storage details. Following that is schema refinement. This crucial step specifies that the data is normalized, a process we'll elaborate on shortly. Normalization systematically helps reduce data insufficiency and conflicts, leading to a cleaner, more efficient, and more robust database design.
Cleaning up the logical structure.
Precisely. Finally, we reach the physical design phase. This specifies the actual physical configuration of the database on the storage media. This includes low-level decisions about file organization, specific indexing strategies, partitioning, and other details that directly impact performance and storage efficiency. This is where the logical design meets the hardware.
A crucial concept in database design, particularly for relational databases, is normalization. What is it, and why is it so important for keeping things neat and efficient?
Normalization is precisely that. A formal method for organizing data within a relational database. It involves systematically separating data into various related tables, resulting in what we call narrow tables, with fewer columns, each focused on a single entity or concept. This is in stark contrast to non-normalized wide tables, which might contain significant redundancy or unnecessary duplicated information.
So breaking big tables into smaller, focused ones.
That's the core idea. The goal is to eliminate redundant data and ensure data dependencies make sense, meaning that only related data is stored together. The advantages of normalization are significant and profoundly improve database health and performance. It fundamentally improves performance by reducing data redundancy, which means less data needs to be stored and processed. It allows for fast sorting and index creation because there's less data in each table to sort and smaller index sizes. You get a larger number of clustered indexes and narrow and very compact indexes, which are highly efficient for data retrieval.
Faster lookups.
Definitely. Critically, fewer indexes per table improve the performance of insert, update, and delete statements because the database has less to maintain when data changes. And finally, normalization leads to less null values and less opportunity for inconsistency, which significantly increases database compactness, data reliability, and overall data integrity. It's about designing for long-term health and efficiency.
And for visualizing these complex designs, there's a powerful and widely used tool, the entity relationship, or diagram. How do these help designers?
Diagrams are indeed indispensable visual tools in database design. An diagram helps designers create databases efficiently by visually representing entities, the key objects or concepts, their attributes, and the relationships between them. Attributes are modeled with their name and connected to the entity or relationship they belong to,
making it easy to see the structure.
Exactly. In the relational model, the final design step, which involves determining the objects whose basic information will be stored and then figuring out the relationships between these groups of information, is greatly facilitated by diagrams. They provide a clear, high-level map that everyone on a project can understand, helping to identify potential issues before any code is written. It's worth noting that while diagrams are invaluable for relational design, this exact conceptual step isn't as explicitly necessary with an object database, as objects intrinsically combine data and relationships in a different way.
A database isn't just a static place where data sits. It's a dynamic environment where information is constantly being added, changed, and retrieved. How do these systems ensure that all these changes are reliable and accurate, even when many things are happening at once, perhaps thousands of transactions a second?
This brings us to transaction management, which is truly at the heart of ensuring reliability and accuracy in a dynamic database environment. A transaction is essentially an event or a logical unit of work that reads values from the database and might also write values back into it. Think of it like a single, unbreakable operation, even if it involves multiple steps.
One logical piece of work.
Exactly. While a transaction can be seen as a type of process, similar to those in an operating system, the fundamental difference lies in their impact. A read operation doesn't change the database's state, but a write operation entirely changes the look and feel of the database. Transaction management ensures that these changes are processed reliably, especially under concurrent access, where many users might be trying to modify data simultaneously.
The cornerstone of reliability in transactions is a set of properties known by the acronym ACID. Let's break down what each of these means because they sound absolutely critical for anything important like financial transactions.
They are indeed the bedrock of reliable database operations, providing critical guarantees. AC stands for atomicity, consistency, isolation, and durability. 1. Atomicity. This property states that a transaction is an indivisible unit of work. Either all the instructions within the transaction will be reflected in the database, or none will be reflected. There's no in-between state.
All or nothing.
Precisely. Imagine a money transfer. If you're transferring Rs10 from account X, initially Rs100, to account Y, initially Rs110, the steps are: read X, X equals X10, write X, read Y, Y will plus 10, write Y. For atomicity, either X becomes Rs90 and Y becomes Rs110, or if any step fails at any point, both accounts revert to Rs100 dial. You never end up with money deducted from X but not added to Y2. Consistency. This ensures that if the database starts in a consistent state, meaning it obeys all its defined rules and constraints, and each transaction, when executed on its own, is designed to be consistent, then the database will end up in a consistent state after the transaction. To achieve better performance, DBMS often use concurrent execution of multiple transactions via CPU system timesharing, but consistency must be maintained throughout, regardless of how complex the interleaving gets.
Maintaining the rules.
Right, maintaining logical integrity.
Yeah.
3. Isolation. This is about concurrency. When multiple transactions execute concurrently and try to access a shareable resource simultaneously, the system must execute them in such a way that there is no anomaly in the shared resource's value. It means that the execution of concurrent transactions should appear as if they were executed serially, one after another, even if they are interleaved in reality.
Like they happen one at a time, even if they don't.
Exactly. Each transaction should be isolated from the intermediate, uncommitted effects of other concurrent transactions. It prevents dirty reads or lost updates. 4. Durability. This is about persistence. If a transaction commits, meaning it successfully completes and all its changes are confirmed, that its effect must persist in the database, even in the event of system failures like power outages or crashes. The changes made by the transaction are permanently recorded to stable storage, ensuring they are never lost.
Once it's saved, it stays saved.
That's the guarantee. It's worth noting that atomicity and durability are often implemented using techniques like transaction logs and shadow copying, where temporary changes are stored in a separate durable area until the transaction is fully committed, guaranteeing they can be recovered.
A transaction doesn't just happen instantly. It moves through various starts.
Yeah.
What are these states that a transaction progresses through from start to finish or failure?
Right. Transactions move through a well-defined life cycle of 6 states within the DBMS. 1. Active. This is the initial state. A transaction is in the active state as soon as it begins executing its first instruction. 2. Partially committed. If the transaction is executed perfectly and has completed all its operations, but the changes are still only in volatile memory and not yet permanently saved to disk, it enters this state. It's approaching its commit point.
Almost done, but not quite safe yet.
Exactly. 3. Failed. A transaction enters the failed state when it encounters an error or a problem that prevents its successful completion. This could be anything from a data constraint violation to a system error. At this point, the transaction is marked for rollback, meaning any changes it has made must be undone. 4. Aborted. This state is reached when the rollback operation is complete. All changes made by the failed transaction have been undone, and the database effectively reverts to its before image as if the transaction never happened. The transaction is fully aborted.
Like it never happened.
Correct. 5. Committed. If no failure occurs and all operations are successful, the transaction successfully reaches the commit point. In this state, all existing temporary values from volatile storage are copied to stable storage, making the changes permanent and durable in the database. 6. Terminated. This is the final stage a transaction will reach. A transaction is terminated if it has either been successfully committed or fully aborted. It marks the end of its life cycle within the system.
What happens when 2 different transactions try to access, or even worse, modify the same piece of data at the exact same time? How do databases manage these potential conflicts to prevent chaos and ensure data integrity?
That's precisely where conflict serializability comes in, a vital concept in concurrency control. It deals with whether instructions in two different transactions conflict when accessing the same data, and if so, how to specify the execution order. Think of it like a meticulous traffic controller at a very busy intersection for data. A conflict arises only if at least one or both of the conflicting instructions are write operations on the same data item.
So reads don't conflict with other reads.
Correct. There are specific rules that dictate how these interactions are handled. If both instructions from two concurrent transactions are read operations on the same data item, they don't conflict. They can take place concurrently in any order without issues, as they don't change the data. However, if one instruction is a read and the other is a write on the same data item, it causes a conflict. In this scenario, the order of execution becomes critical.
Right.
If the read occurs first, it will read the old value before the new value is written. If the write occurs first, the data item is updated, and then the read instruction will read the newly updated value. The database must ensure a consistent outcome by enforcing an order.
Order matters there.
Definitely. If both transactions are write operations on the same data item, they are in conflict. But interestingly, they can technically take place in any order, because the transactions themselves don't read the value updates for their own logic within that specific operation. The value that ultimately persists in the data item after the process is over will simply be the one written last. The system ensures a defined final state, though the intermediate state might vary depending on the exact interleaving, but this is handled by isolation and durability properties. These rules help the database maintain a logical and consistent state even with high concurrency.
Moving from managing changes to optimizing retrieval, when you ask a database for information, especially with a complex query across multiple tables, how does it know the fastest way to get you that data? Does it just guess, or is there a clever system at play?
The optimizer. That's where the magic of query optimization happens. It's a crucial, complex process used in relational DBMS to determine the single most efficient way to execute a given query. When you submit a query, a component called the query optimizer springs into action. It doesn't just guess, it rigorously evaluates multiple possible execution plans, different sequences of operations to fetch the data, and then selects the one with the lowest estimated cost, measured in terms of time and system resources like CPU usage and disk I/O.
Finding the cheapest path.
In terms of resources, yes. The need for this arises because databases can be incredibly complex, especially with non-trivial queries involving many tables and conditions. The same data can often be accessed in many ways, using different data structures, indexes, or join orders. Each method can lead to vastly different processing times. A seemingly simple query might take seconds if optimized well, or it could take hours if a poor plan is chosen. The optimizer's role is to automate this extremely difficult decision-making, aiming to find an optimal or at least a near-optimal execution plan that minimizes the response time for the user. It's challenging because finding the absolute best plan among all theoretical options is often computationally impossible or impractical for large databases, so optimizers aim for a plan that performs reasonably well and is close to the ideal.
One of the key challenges in complex queries, especially for the optimizer, involves joining multiple tables, bringing disparate data together. How does the optimizer decide the best way to do that efficiently? There must be so many possibilities.
You're right. Join ordering is a core and highly complex part of the optimization process. This algorithm typically works in two stages to find the most efficient path. 1. First, the optimizer evaluates all possible ways to access the initial data from each individual table. A relation, or table in the query, can be accessed by performing a sequential scan reading every single row, or by using an index, which is much faster if applicable and matches the query's conditions.
Scan versus index lookup.
Exactly. The optimizer records the most cost-effective method for scanning each individual relation, while also preserving any desired sort order requested in the query. 2. In the second stage, the optimizer then iteratively considers combining each pair of relations based on their join conditions. It takes into account the different join algorithms available within the DBMS, such as nested loop join, hash join, or sort merge join, each with its own performance characteristics. It records the most efficient way to join each pair, again including the cheapest method that preserves any desired sort order in the result. For queries involving 3 or more relations, the process becomes iterative. The optimizer constructs larger plans by joining existing 2-relation plans with the remaining relations in the query, continually seeking the most efficient combination until the final, comprehensive query execution plan is built. It's a bit like solving a giant multidimensional puzzle to find the quickest route.
How does the optimizer actually estimate these costs? It sounds like it needs to predict the future somewhat, anticipating how much time and resources a given path will take.
Cost estimation is indeed one of the toughest problems in query optimization, and it's less about predicting the future and more about sophisticated statistical modeling. Optimizers use complex mathematical models to predict execution costs for each potential plan. These models heavily depend on accurately estimating the cardinality, which is essentially the number of tuples or rows that will flow through each part of a query plan.
How many rows it expects at each step.
Exactly. Cardinality estimation, in turn, relies entirely on estimating the selection factors of various conditions or predicates in the query how many rows will remain after a specific filter is applied. For this, database systems estimate selectivity by maintaining a fair amount of detailed statistics on the distribution of values in every column, often using things like histograms. While this technique works remarkably well for estimating the selectivity of individual conditions, the real challenge arises with complex queries that have conjunctions of predicates, multiple conditions linked by and or. This makes it very hard to accurately estimate the selection of the combined condition, especially if there are hidden correlations between columns. Correlations make it tricky. Very tricky. This difficulty often leads to less than perfect cardinality estimation and uncaught correlations between data, which are main reasons why optimizers might occasionally pick less than optimal query plans. This is why it's incredibly important for database administrators to regularly update their database statistics, especially after major data loads or significant changes to the data, to provide the optimizer with the most accurate information possible for its calculations.
No system is perfect, and failures inevitably happen. Whether it's a sudden power outage, a software bug, or a physical system crash, how do databases manage to bounce back and ensure your valuable data isn't lost or corrupted? It feels like magic, but there's clearly a sophisticated system behind it.
This is where crash recovery steps in, an absolutely vital function in any reliable database management system. Crash recovery defines the precise process of restoring the database to a consistent and usable state after any type of failure, be it a system crash, a power failure, a disk error, or a software bug. Its major function is to ensure data integrity and, critically, durability, meaning once data is committed, it stays committed.
Durability from ACID again?
Exactly. These are fundamental parts of the ACID properties of a transaction, ensuring that even in the face of disaster, your data remains whole and correct.
Why is crash recovery absolutely essential for any reliable database system? Couldn't you just restart it and pick up where you left off?
Just restarting it isn't enough, and it could lead to catastrophic data loss. During a crash, ongoing transactions may not have completed properly. This can lead to a number of severe issues. Incomplete updates to the database, where only part of a transaction has been saved, leaving the data in an inconsistent state. Outright data corruption, where the database becomes unreadable or unusable, or a generally inconsistent state where the data no longer reflects logical business rules.
Like that half-finished money transfer.
Precisely. Imagine a financial transaction where money is deducted from one account but never added to another due to a crash. Without proper crash recovery mechanisms, data loss or integrity issues would be a constant, unacceptable threat, making the database completely unreliable for critical operations. It's the database's built-in insurance policy.
So what are the key concepts and tools that enable a database to perform this seemingly miraculous recovery from a crash? It sounds like there must be some kind of detailed historical record of everything that happened.
There is, and it's built on a few core concepts that form the database's memory of events. 1. Transaction logs. The DBMS continuously maintains a meticulous log file. This log records all details of every operation performed by transactions. Crucially, it includes before images, BFAM, which is the state of the data before any change, and after images, AFM, the state of the data after the change, along with the transaction ID and the operation type. These logs are the most important mechanism for correctly undoing operations from incomplete transactions or redoing operations from completed but unsaved transactions during recovery.
The database's diary?
A very detailed diary, yes. 2. Undo and redo. These are the primary actions performed using the log. Undo operations revert the changes of incomplete transactions, ensuring atomicity, as if they never happened. Redo operations reapply the changes of completed transactions that might not have been saved to disk due to the crash, ensuring durability. 3. Checkpoints. A checkpoint is a specific point in time where the DBMS systematically saves the current state of the database to disk and records an entry in the log. This is a crucial optimization for recovery. During recovery, the system can start scanning the transaction log from the last checkpoint rather than having to scan the entire log from the very beginning of time, significantly speeding up the recovery process. So robust crash recovery relies heavily on maintaining these detailed transaction logs and intelligently using checkpoints to create efficient recovery points.
The recovery manager is the component that makes all this possible, orchestrating the bounce back. What are its functionalities?
The recovery manager is indeed the unsung hero that ensures both atomicity and durability during database operation and after a crash. It's comprised of specialized modules responsible for logging all changes and performing the necessary recovery procedures. During normal operation, it ensures every transaction's actions are meticulously recorded in the transaction log.
Logging everything.
Everything important. When a crash occurs, the recovery manager springs into action. Its core functions include analyzing the log to understand the state of the database at the time of the crash, identifying which transactions need to be undone and which need to be redone, and then systematically performing those undo and redo operations to bring the database back to a consistent state. It also manages checkpoints, periodically flushing data to disk, and marking the log, significantly shortening the recovery time. It's essentially the database's emergency response team.
Finally, let's zoom out to how databases have had to adapt and evolve to integrate with the massive changes brought by the internet and the web. This must have been a truly revolutionary shift for database systems.
Oh, it was a monumental, transformative shift. The rapid adoption of the web and the rise of Java programming fundamentally changed computing as we knew it. While the core content of databases itself, the way data is structured and stored, was largely unaffected at its deepest level, DBMS had to profoundly adapt by incorporating web interfaces and Java constructs to become accessible and function seamlessly over the internet.
Databases had to get web savvy.
They absolutely did. Traditional DBMS often assumed a world where dedicated IT staff were responsible for everything: naming conventions, creating directories, defining data types, indexing, integrating disparate systems, and manually managing applications. However, with the internet, data and its applications are often created and maintained by far fewer people, and accessed by millions, demanding more automated, self-service, and highly accessible systems. Internet protocols themselves have evolved significantly to support data caching on the network through intermediate proxies and on client systems. This significantly improves response time by reducing the need for constant, direct access to data across the network, making web browsing feel faster.
Caching helps a lot.
Immensely. Communication protocols also now support robust firewall systems and incorporate public key encryption for enhanced security, which is absolutely vital for transmitting sensitive data online. Crucially, programs can be downloaded by users through simple interfaces that offer a consistent experience across various operating systems and devices. All of this required significant infrastructure changes to manage heterogeneous data types and the complex web of links between them, leading to the evolution away from purely dedicated, isolated servers towards more distributed, flexible, and internet-aware architectures.
Can you give us a concrete example of a web application and its components that clearly demonstrate these database-internet interactions in a real-world scenario, perhaps something like an e-commerce prototype? Certainly. An e-commerce prototype built with JSP, or Java Server Pages, clearly illustrates the seamless interaction between web and database. It typically starts with an index page, index.jsp. This is the entry gate for users, often featuring a welcoming message and a link that takes them to various option pages where they can begin browsing products or services. From there, users navigate to the products page, products.jsp. This page dynamically displays all the available products or options, retrieving details like names, descriptions, and prices directly from the database. This is where users interact, adding items to their virtual shopping cart. Each listed option would have a dedicated Add to Cart button, and there would be a running count showing the number of items currently in their cart, usually maintained in a temporary cookie or session. Pulling product info live from the database.
Exactly. Once items are added, users might go to the cart page, part.jsp. This page dynamically retrieves and shows a full list of all items in the cart cookie or session, along with their details. The list for each item typically includes the option name, its price, a text box for quantity adjustments, and a button to remove the item from the cart. This page usually features 3 more crucial buttons: one to continue shopping, a second to update the cart with any alterations, and a third to proceed to place or confirm the order.
Managing the temporary cart state.
Right. Finally, there's the confirm page. Confirm JSP. This page displays the final order list, often pulling updated totals and shipping information, prompting the user for a last review. On this page, there are usually two buttons, one to cancel the order, and the other to definitively submit the complete order to the database for final processing and fulfillment. This entire flow relies on constant, seamless, and secure database interactions behind the scenes.
Briefly, what are some of the underlying technologies that make these web applications tick with a database, ensuring that data is served efficiently and securely over the internet?
There are a few key technologies involved that bridge the web and the database. CGI, or Common Gateway Interface, provides the mechanism for how the web server communicates with other programs on the server. CGI programs are used to process HTML form data and interact with the database. However, a significant performance flaw with traditional CGI is that each page request typically creates a new process on the server, which scales poorly when there are many concurrent requests, leading to slow performance for popular sites.
The old way, not very efficient.
Not for high traffic, no. The web server itself, like Apache or DingSync, controls the initial interaction with the client's web browser, handling HTTP requests for web pages. But for more complex dynamic applications, application servers are crucial. They're used for maintaining persistent processes to handle requests and act as middleware, sitting intelligently between the web server and the database systems. These application servers eliminate the conflicts and overload associated with creating a new process for each request, and they efficiently maintain session state information, which is vital for interactive web experiences like shopping carts.
Application servers are the modern middleware.
Largely, yes.
Yeah.
Lastly, the XML document is fundamental for structured data exchange, especially between different systems or layers of an application. It follows specific rules, often defined by a DTD document type definition or XML schema, to ensure structured data. For an XML document to be well-formed, meaning syntactically correct and parsable, it must adhere to three main guidelines. It must initiate with an XML declaration. It must consist of a single root element that contains almost all other elements, and all elements within it must be properly nested in order, ensuring a consistent and reliable structure for data transfer. These technologies collectively enable the dynamic, data-driven web applications we use every day.
Wow, what an incredible journey we've taken today. We've gone from the fundamental definition of a DBMS and its fascinating history, tracing its evolution from rigid navigational systems to the powerful relational model.
Quite a trip back in time.
Yeah. We then navigated through the intricate layers of database architecture, explored the conceptual power of various data models, especially the revolutionary relational model, which underpins so much of our digital world, and truly understood the expressive language of SQL, the commands that bring data to life.
SQL is key.
Absolutely. We then delved into the meticulous process of database design and normalization, the crucial safeguards of transaction management and crash recovery that ensure our data's reliability, and finally looked at how these systems have seamlessly integrated with the internet to power our daily digital lives.
It's been a truly deep dive, and my hope is that you now see beyond just the technical terms. This deep dive wasn't just about acronyms. It was about understanding the invisible, intricate dance that manages virtually every piece of information we interact with digitally.
The hidden machinery.
Exactly. It's about the silent orchestration ensuring speed, accuracy, and security in a world that is fundamentally built on data. Without these robust, constantly evolving systems, our digital experiences would be slow, unreliable, and prone to chaos stable. Truly, modern life as we know it would grind to a halt.
So next time you open an app, make an online purchase, or check your grades, take a moment to appreciate the immense orchestrated power of the database management system working tirelessly behind the scenes. It's a testament to incredible engineering and a constant evolution. It makes you wonder, what other unseen systems power your daily life that you're now curious to deep dive into? We'll see you on the next deep dive.